All right. Good morning again, everyone. Today we will actually we'll start with probably your questions about homework three, which by the way is due later, right before midnight. Of course, that's for the markup, but again, you can submit until the last day of classes, which I guess is when? Is it August 9 or 14? I think it's August 9 if I'm not mistaken. So I guess we still have 3 more weeks for the course. And actually, I think we are still on a good pace to cover at least some of the things that I believe to be important for any linear algebra course. So yeah, though hindi ko na itatackle yung super theoretical parts because again, I don't want to double burden you with the abstract algebra thing mixing together with linear algebra. All right. So again, homework three will be due tonight at midnight. So we'll start with your questions, and then after, if you don't have too much questions, then probably we can start talking about module three, which is about linear transformations. But before I started the recording, there was a question about homework three, problem number one. So in problem one, so I gave you distinct elements of a vector space V, say V1, V2, and V3, and there are given alphas from the field. Notice that there are no much restrictions on the V's and the alphas, aside from the V's being distinct elements, right? So the question is, under what conditions is D a linearly dependent set? Probably I should clarify this one. There could be several conditions that you can think of to guarantee that D will be linearly dependent, but it will be sufficient to give me one. It could be a very specific imposition on V's or the alphas. So, ang assumption lang natin about the V's, dapat sila ay distinct. And then there are no other restrictions from the alphas. So if you can give me some restrictions or some conditions on the vectors, or even with the alphas, or both of them, na magaguarantee nyo na yung set D will be linearly dependent, then that's fine. You don't need to exhaust all possibilities or give me a very generic or encompassing condition to ensure that D is linearly dependent. It suffices to give me a specific one. Actually, and that's fine. So,
Okay. So,
basta bigyan nyo
sir,
ako ano yung pwede
sir,
kong i-impose kay V's and or kay alphas.
sir, no need to be rigorous about it. Parang covering just specific. Pwede kayong magbigay just one condition
Yes?
na, okay,
Right. So, kahit anong condition, basta ma-preserve nyo lang na yung mga V's ay distinct.
distinct.
So, other than that, you can give me conditions on alphas, tas wag nyo nang pakialaman yung V's, or you can give me conditions on V's, wag nyo pakialaman yung alphas, or you can be creative with both. So as long as these are from arbitrary vector spaces and the scalars alpha.
So, you're talking of alphas, not just the alphas here in the D, but the alphas that we will need in the linear combination involving D.
Mhm.
Okay.
Well, yung scalars na gagamitin nyo dun sa linear combination is a different thing. Kasi di ba para maging linearly dependent, dapat ay makahanap, linearly dependent, kailangan, basta may isang non-zero, right?
Opo.
So, yeah.
Okay, sir. Thank
Pero,
you.
uh, actually, you cannot, do not give conditions for the betas. So, kailangan ko, bigyan nyo ako ng ano dapat yung properties na meron kay V1, V2, V3, and or alpha 1, alpha 2, alpha 3, so that when you form the homogeneous equation with the scalars beta, halimbawa, beta 1, beta 2, and beta 3, if you solve that homogeneous equation, you'll be able to find beta 1, beta 2, and beta 3, not all being zero at the same time. That will make that homogeneous equation. And that would be enough. Right?
So parang, sir, we start with the assumption that the betas are not all zero. And then we look at what should be alpha 2 and V's such that those betas won't be all zero. Ganun ba, sir?
Yes, that could be one approach.
Okay. Sige po.
Or pwedeng, yeah, I see what you're saying. Pwede ka sigurong magsimula sa magbigay na ng specific beta 1, beta 2, and beta 3, not all being equal to 0. And then you solve reverse in a reverse fashion. What would be your alphas and the V's, right? So pwede rin yan.
Okay. Thank you, sir.
Right. And again, you don't need to be very generic about your condition. It could be a very trivial condition. Actually, there is one na hindi ko kagad naisip. That's why I needed to rewrite my answer key to this particular problem, just to account for that one trivial solution. But other than that, yeah, you don't need to be very rigorous about it. Okay. Right. Any other question about homework 3? Meron pang may clarification?
Sir, sa number 1 po,
Okay, what about number 1?
sabi takalawa na condition siya that V1, V2, and V3 be distinct elements. So can I give distinct elements for V1, V2, and V3?
Hindi ka pwedeng magbigay ng specific vectors V1, V2, and V3 because yung vector space ay arbitrary.
Okay.
So if you're saying that you will give, say, matrices V1, V2, and V3, or elements of R3, say V1, V2, and V3, na magiging linearly dependent
Dependent
yung
siya. So, okay.
hindi pwede yon kasi my assumption here is I'm working with a vector space V, which is generic.
Okay.
So, hindi pwedeng mag-specify. So, pwede nyo gawin, magbigay kayo ng relationship between V1, V2, and V3, and possibly yung mga alphas pwede nyo rin paglaruan so that the set D will be linearly dependent.
Okay po.
Right? Siguro medyo nag-overthink kayo sa problem 1 because when I did the solution, I was trying to get a very generic condition for the vectors and the scalars. But after some thought, meron palang mas madaling solution. Kasi wala naman sinabi yung problem that that I should be generic about it. So yeah, you can think of a very trivial solution. Just guarantee that you maintain that V1, V2, V3 are distinct elements of an arbitrary vector space V. All right. Okay. Any other questions? Let me see. Okay. A lot of you already got problem 2, which is good. There are a couple of submissions for problem 3. Yeah, and then problem 4. Again, I hope you got the correction or the further clarification of problem 4. Here, we want to show that the set curly B is a basis for this set of matrices over the complex numbers. I forgot to specify over which field we are dealing with. Let's just pick the easier field. So yung scalars magaling set of complex numbers, okay? And then again, the last statement is just a trivia that these matrices, as simple as they are as mathematical objects, they play a very important role in quantum physics. Though I don't know anything about quantum physics, but probably it's a good footnote to add in here. And then problem 5, kokonti pa lang yung nagsasubmit about problem 5. Probably this is one problem that you guys are avoiding. But okay, so here it is a question whether the set of all FAs is a basis for the vector space F. Now, I hope you guys see what or how the function FA looks like. Actually, FA can be thought of as the characteristic function. So if you're more familiar with it, so this is the characteristic function of the element A. So ibig sabihin, it assigns 1 whenever the argument of your function x is equal to a, and it is 0 otherwise. Just be careful when treating this set. This set has infinitely many elements because your a can be any real number. So that means one example of of an element of this set is f1. F1 is the function that assigns 1 when x is 1 and 0 elsewhere. So ang graph niya, kay x equals 1, ang value niya ay 1, pero all else ay 0 yung function value. So meron kang hold dyan. So yun yung graph niya. Then F2 would be somewhere here. May point ka dyan. Pero again, meron ka, perhaps I'll use a different color. So 1 siya dyan, and then 0 siya elsewhere. Then even f sub 1/2. So f sub 1/2 of x, it assigns 1 to 1/2. So, sorry, mali pala yung plot ko dito. Oops. Dapat yung blue ay na kay 1 din. Right. Ito siya. And then at 1/2, okay, this is x equals 1/2. Function value at 1/2 is 1, but it is 0 elsewhere. So this functions fa only has one non-zero element. So you can think of it as sort of an extension of, or as an attempt to extend the notion of elementary basis. So you have in elementary basis we assign 1, especially for Rn. We assign a non-zero value which is equal to the unity of the field to the ith position of your n tuple, right? So this is an attempt to try to generalize that. So using the characteristic functions of A, and you see here that okay, graph nyo siya, ganito yung itsura. You do it for every real number. But the question is, if I try to generalize the notion of elementary basis this way, set consisting of infinitely many functions, as many as real numbers there are, can I get a basis for the vector space of all functions from R to R? Okay. Now, I think I mentioned it last time. A clue to this one is that just keep in mind that when we are talking about linear combinations from an algebraic point of view, we define a linear combination to be a finite summation. Remember, we say that a linear combination is something of this form, alpha I, I going from 1 to n, and n is a natural number. So we don't allow summations of this form. So I going from 1 to infinity, this is not a linear combination. So a linear combination must terminate at a natural number n. So it could only have a finite number of terms. All right. So that's the clue here. And probably you can read between the lines. You already know what the answer to number 5 is, whether it's a basis or not. But again, you can use that hint that a linear combination must take only a finite number of terms. All right. And then problem 6, you have to do 2 things for problem 6. You need to show that set A is linearly independent, and you need to extend it to a basis for the set of polynomials of degree 5 or less. Now, just remember that if you are extending A, I want to see a proof or an argument that will convince me that the new set that you formed or the extension that you formed will indeed constitute a basis for P sub 5x. So if you happen to insert 1, 2, or 3 elements to A, you must show that the new set that you form would be linearly independent, and it should span the set of all polynomials of degree 5 or less. or you can use any of the other characterizations of basis that we gave in the module. So you can have several approaches to this. Some of you guys showed that any polynomial can be written uniquely as a linear combination of elements of A plus the other elements that they added to the set. Some used what? Yeah, some use the argument about the dimension of this vector space, because this is, I think, one thing I forgot to mention about last time. I was I think in a hurry to finish the meeting, but I forgot to mention that the number of basis elements is called the dimension of the vector space, and the dimension is well defined for any vector space because number one, any vector space has a basis. We stated it as a corollary, though without a proof, but let's accept that to be a fact. And that second, any two bases for the same vector space have the same number of elements. So well defined yung pagiging yung dimension ng isang vector space, right? So and I guess in one of the examples I mentioned what is the dimension of P sub 5. So if you can discern from the notes what's the dimension of P sub 5, you can readily see whether this is enough to be a basis or not. And then you know how many elements to put into the set A. Some of you did that. Um, look at the dimension and see how many elements more should they add to A, and then use Steinitz replacement theorem in order to find the additional elements, right? But yeah, it's up to you which approach you want to take. Somebody raised her hand. Yes, Mamrina, you have a question?
Sir, may question po. Sir, so ibig sabihin nun kung ang dimension po niya ay 5, pwede po kami mag-add ng isang vector like x to the 5th plus kung ano po yung missing na polynomial.
Yep.
Okay po.
Yeah,
Thank you.
pwede nyo gamitin yon. Though be careful kung ano yung tamang dimension.
Okay po. Thank you po.
Alright, so yeah, pwede nyo tingnan yon. In the notes, I think I mentioned, hopefully sana tama yung pagkakastate ko. I'll take a look at it later. Hopefully no typos there. But if you know what's the dimension of P5, you know how many elements you need to insert into A or add into A in order to get a basis. Because of course, in the first problem, it will show that this is linearly independent. Okay. So tapos sabi natin, pag alam mo yung dimension, tapos ganun kadami yung laman ng isang linearly independent set, then that linearly independent set constitutes a basis for the vector space. Right? Okay, other questions? So, yeah, I hope to see submissions later tonight. Probably I'll again work overtime to give it back as soon as possible to you guys. But of course, if you cannot finish it, that's fine. You have until the end of the last day of the last day of classes for the semester to submit everything. All right. Now, oh, by the way, after that, you can start working with homework 4, which is in module 3. I extended the deadline for the homework. I proposed that we have the deadline for homework 4 on Tuesday. Binilang ko, so that would be 6 days. Actually, that would be 6 days from tomorrow, so 7 days from now. So that will give you Thursday, Friday, Saturday, Monday, and Tuesday. Ano sabi ko? Tuesday pala. Tuesday ko sinet yung deadline. So you can just allot 1 day per problem. So there are 5 problems to this homework. So yeah, you have 1 day. I didn't count Sunday, so you can have a day off on Sunday. But yeah, you can do at least 1 problem a day. Then you will be in good shape to finish module the homework number 4. All right, so if there are no other concerns, then let's try to browse through at least half of module 3, okay? Let's see. So module 3 talks about linear transformations because primarily linear algebra is the study of the structure preserving maps. So kahit anong algebra, maybe I should put that into some notes here. So algebra basically is, I don't know if you already talk about it in modern algebra, but most of modern algebra is about the study of structures. Because before, classical algebra is meant to be the study of equations. When will equations have a solution over some specific fields, rings, groups, or any other structure, right? So that's the concern of classical algebra. But again, so they started with the basic linear equations. Then we know how to solve linear equations. You have, and then you go a degree higher. You look at quadratic equations, and somebody derived the quadratic formulas for that. And then even cubic equations, they can be solved by a closed form formula. And then quartic equations or degree 4 equations, they do have a closed form formula. All right. Uh, Tama ba? Quartic nga ba yun? I think, let me check that. Pero, yeah, basically, classical algebra, which equations have solutions over specific fields. But come quintic equations, though I need to check that. Is it quartic or quintic? But for quintic equations or degree 5 equations, people are trying to solve still for an implicit solution, an explicit solution for quintic equations. But somebody proved, I think it was Galois, but you also need to fact check me on that, proved that there is no closed form solution, that you cannot find an elegant explicit solution for quintic equations in terms only of the coefficients in your system or in your equation. So that that actually effectively rerouted the focus of algebra. So that basically is the transition from classical to modern algebra. So instead of studying equations, which was found to be futile because not all equations can be solved purely in terms of the coefficients of the polynomials. So people dropped that, and any search was deemed to be in vain. So they started inventing this type of thing, which we are now calling modern algebra, which is basically the study of structures, how objects behave in a group or in a more rigorous or in a in a more rigorous fashion. So titingnan natin ano yung properties ng structure na yon when we put operations to it, when we put or when we impose certain properties on those operations and on those sets. So basically that's where the study of groups, rings, fields, and so on started. So basically modern algebra study of structures. So whenever talking about algebra in the modern sense, so you study structures. But what do we study? Well, we study structures that are preserved use under certain mappings. Now, linear algebra, from the name itself, linear meaning these are linear maps. All right. So basically, this is the study of structures that are preserved under linear mappings. And Module 3 talks about what do we mean by linear maps. So basically, you will see that linear maps, basically, these are mappings or functions between two vector spaces that preserves the structure of the vector spaces. And we'll see later exactly what I mean here. But before going to the module, let me just emphasize one thing, because in the past homeworks I asked you to prove some things about functions, right? So, but I want to emphasize the difference between, say, f and f of x, right? So if little f is a map from f to v, then it should be clear that when I ask you what is the function, you will just say f. So f is the function because a function is a map, and f is what is defined to be the map. And f of x is not the function, but it is just an element of the codomain, right? And again, just again to emphasize, the set V here is not necessarily the range, but this is the codomain. And the range is simply a subset of the codomain. So when you write a function or a map this way, you are just saying that every element of curly f, which is your domain, is mapped to an element of V. But you are not claiming that all elements of V have a pre-image in curly f. So merong ilan na gumamit ng term na range for the second set in the definition of a map. Be careful, it's just a codomain because we are not sure if this is indeed the range. So basically, that is just a superset of the range. And again, I hope that this is clear, or it is yeah, at least starting now, that when you write f of x, this is not a function, but this is an element of your codomain. F of x is a specific value, so it is a value. It is the value that you get when you plug in x into your map f. And then if I'm asking about the function, then the function is simply f without the argument x. And having said that, when we prove, say, commutativity or associativity of functions, of function addition or scalar multiplication, um, we do it this way. So, di ba, for say for commutativity, okay. So we say that an operation is commutative over a set if so plus is commutative on, say, f if and only if a plus b is equal to b plus a for all ab in f, right? So this is the definition of commutativity. So we will check whether two elements commute or the ordering of the two elements which we are adding is not relevant or it is immaterial insofar as the performance of the operation is concerned, right? So when you talk about functions, so if you want to show that um, curly f, the set of all function, addition, usual addition is commutative on curly f, then the way to do it is to consider two functions in curly f, f and g in curly f, such okay, and show that f plus g is equal to g plus f. I guess some of you are hesitant to write the statement this way kasi hinahanap nyo siguro yung argument na x. But this is the proper way of writing what do you mean by commutativity. So you add two elements of your set. The set here is the set of all functions. I add two functions, f plus g. It should be equal to g plus f, right? But how do we show equality of functions? So f plus g is a function on itself. G plus f is a function on itself, where addition is defined this way. The map f plus g. We are not adding any element here, any mapping yet, but we are adding two functions or defining what is the map f plus g. F plus g actually is a function from f to a vector space such that f plus g of x. So you see here that this is also a proper way of writing the image of x under the mapping f plus g. Though probably in elementary algebra classes, we're used to put in parentheses here, just to remind us that sort of the x comes inside the sum. But the formal way of writing it is f plus g because f plus g is itself a map, right? So ito yung pangalan ng function. Ipa-plug in ko si x sa kanya. And the definition of usual addition is that this is equal to f of x plus g of x. All right? So that's how we define the addition map. And two functions are equal if and only if their function values for all elements of the domain are equal to each other. So if you want to show this, that is equivalent, right? This is equivalent to showing that f plus g of x is equal to g plus f of x for all x in your domain. So actually mali pala yung sinulat ko dito. This should be say a field f, for instance. So for all x in your domain. Okay, so that's why you see in the proofs that I am plugging in values for x to the left side and to the right side coming from the domain, and I show that for any arbitrary choice of function of element in the domain, the function value remains the same. All right. So again, this is equivalent to saying that f of x plus g of x is equal to g of x plus f of x for all x in the domain. Okay, and if you're able to show this, then you can conclude that f plus g is equal to g plus f because your choice of x in your solution of this in showing this identity is arbitrarily chosen. So yung iba hindi na sinusulat ito. Probably I also did not write it in some of my proofs. Yeah, probably I just assumed that to be clear. But just to be clear for some of you, if it's not too clear how we formally write things. So from here, we were able to conclude that f plus g is equal to g plus f. Again, by definition of equality of functions, two functions are equal if and only if the function values for each element of the domain are equal to each other, right? And then it should be clear that f plus g is the formal way of writing the sum of the functions f and g, wherein we do the usual addition of the images. Kaya minsan, if you do f plus g, and then you just say, because of commutativity, you need to specify commutativity over what set. So here, this happens to be true because of commutativity of addition on the vector space. Okay, so I just want to touch a little bit on this because in this module, we'll be talking about functions. And usually we will write proofs involving functions. So gusto ko lang maging clear paano yung formal na pagsusulat. Though sometimes I again omit some of the details or some of the formal things because I assume that that is clear. But if not, then para lang masanay kayo, you can include all those details. So let's start. Linear transformations. So again, linear algebra study of the structure of structure of objects under maps that preserve certain properties. At ito na yung gusto nating i-preserve na properties, the linearity property. So we start with definition 7, how we define linear transformations. So we start with two vector spaces over the same field F. So say V and W. Then a function L with domain V and codomain W is a linear transformation, or another term for a linear transformation is a homomorphism, if and only if for all V1 and V2 in V and alpha in F, the following conditions are satisfied. So condition 1 just says that the image of a sum is the sum of the images. And then condition 2, the image of a scalar multiple is a scalar multiple of the image. And usually condition 1 and 2 are collectively known as the linearity property of the transformation L. So if you want to prove that the function L is a linear transformation or a homomorphism, then you need to check two things. Again, when you're trying to prove that this is satisfied, you only work with one side of the equation. All right. So either start with L of V1 plus V2, use the definition of L to solve for its value, possibly rearrange some terms, and ultimately show that LV1 that is equal to L of V1 plus L of V2. Or do it the other way around, compute L of V1 plus L of V2, compare it with what is the expected L of V1 plus V2 from the definition. And the same thing goes for property 2, which is about scalar multiples, all right? So you see by the way linear transformation are defined, parang na-preserve yung property ng vector addition and scalar multiplication. Though there are actually 4 operations involved here. the addition and scalar multiplication in the vector space V, and then the scalar multiplication and the vector addition on the vector space W. So, pero if it's a linear map, then vector addition is preserved because here you see that when you add two elements of V, say V1 and V2, if you want to take its image, of course, this guy's an element of W. But if L is a linear map, then you can simply compute for the image of V1 and V2, and then just add them up. All right? And same thing goes for scalar multiplication. So na-preserve ng linear maps yung structure ng vector space because addition is kind of preserved. The image of a sum is the sum of the images, and scalar multiplication is also preserved. You have the image of a scalar times the vector is equal to the scalar times the image of the vector. All right? Okay, I have here remark number 3, which is about showing that this is a nice property. It further confirms that linear maps kind of preserve the structure of the vector spaces, such that if you have a linear map or a linear transformation, the image of the zero vector in V is the zero vector in W. So I put this as a remark in blue box. So that means I want you guys to think about this. Or actually, do you have any idea how to prove this one? So here, given a CLI linear transformation. So what can you suggest we do in order to show that the image of the zero vector is another zero vector? Any idea? Or you guys didn't have the time yet to go through module 3?
You can use the properties for linear transformations, or I think you use a scalar multiplication to show that the zero vector is in V, then try to and compare that one to the zero vector in W using by multiplying it with zero. I know I forgot my train of thought, but something along that line.
Yeah, probably we can work with that. That's a good idea. So you're suggesting kunin ko yung image ng 0 times any vector? Or any vector V?
Yes, any vector in V, then show that it's the same one in W.
Yeah, let's see if that will work. Because this is L of 0 on V, the zero vector in V, right? And the zero vector can be written as the 0 in the field times any vector, right? So, alam na natin to from before, right? And then since we know that L is a linear map, then pwedeng lumabas yung scalar mula dun sa loob, right? So we can write it as 0 times, so this 0 here is the 0 scalar over the field times L of D. Now, just be careful that the multiplication here is the multiplication in the codomain W. But nevertheless, we know that W is a vector space, right? So again, I think in one of the propositions, we said the 0 scalar times any vector element will give us what? That will give us the 0 vector in W, right? So yeah, I think that's a good idea, Jen. Nice one. So we have proved that the image of the 0 vector in V is the 0 vector in W, if L is, of course, a linear map. Anybody else who has an alternative proof? Because actually, this is not the proof I'm thinking of, but nice idea there. Anyone else who has an idea? What would be an alternative proof for remark 3? So bawal na yung scalar multiple. Nagamit na ni Jeng yon. So what do you think? The nice thing about our position right now is that we don't know anything much about linear maps. Ang alam lang natin about linear maps ay yung definition. So probably we can play with the definition. So maybe I can try, how can I apply property 1 in order to come up with an alternative proof for remark 3? So probably let me start this way. So since I want to compute the image of the zero vector in V, let me think about what could be two vectors that I add to each other to get the zero vector. And of course, that's fine because I can take any vector from V, and I know since V is a vector space, it will have an additive inverse, right? So that means the zero vector, I can write it as V1 minus V1 for any V1 in V. Right? Kasi si negative V1, siya yung additive inverse ni V1. So when I add them up, I get the zero vector in V. All right? Then I'm going to use the linearity property. Because again, remember that I can write it as V1 plus negative V1. Just to be strict about it. And then I can use linearity. So this could be LV1 plus L of negative V1. Okay? And again, it should be clear that the addition here is addition on W now, because this is an element of W, this is an element of W. But again, I can appeal to the linearity of L and write it as negative V1. All right? And I guess this is what we wrote in the last problem in homework 2, I guess, na ang additive inverse ni negative ang additive inverse ni A ay negative 1 times A or something to that effect, right? And note that this is exactly our notation for the additive inverse of LV1. LV1 plus its additive inverse will be the zero vector. Okay. So that's another possible proof for remark 3. Okay? Now, yun yung kagandahan sa simula ng isang mathematical discourse. Kakunti pa lang yung theorems or definitions. Kakunti pa lang yung pwede nating paglaruan. So, dapat, with that, magkakaklu kayo ano lang yung pwede kong laruin or what can I manipulate in order to get the result that I want. Okay? Now, the next few examples give us specific linear transformations or simple linear transformations. Example 33 tells us that if you have a fixed alpha from your field of scalars, then scaling all vectors in V by alpha is a linear transformation. So L of alpha is a specific linear map with a fixed alpha. So if you scale your vector, all vectors in V by the scalar alpha, then what you get is a linear transformation. So I guess the proof here is straightforward. So you can practice with example 33, showing that this is indeed, or L sub alpha is indeed a linear transformation. Again, all you need to do is to check condition 1 and condition 2, right?
Sir, sir,
Mhm.
would it be
Yes.
all right if you could, for example 33, show us how you will go about the proof of the linear transformation so that we will have a guide for the next?
Yeah.
Thank
Right.
you, sir.
Yeah, I plan to do some examples of proving that a certain function is a linear map. Though skip ko yung 33 kasi straightforward naman siya. If you see an example that I'll do later, then you can probably write your own for 33. So I'll try to do the more challenging ones. Mhm. Okay, and then 34 is another example. So here you have F2, set of all ordered pairs over the field F. And then the codomain is the set of all triples over F. Then the function L, which assigns to the vector v1, v2, this 3 vector with fixed alpha 1 until alpha 6. So yung alpha 1 and alpha 6 are fixed elements of F. It is said to be a linear transformation. Again, this is sort of mechanical, so I'll skip this one. but show an example later, yung mas challenging. But I hope you can try to write your own proofs. Kasi I think most of homework 4 will ask you to prove that a certain map is a linear transformation. So maganda rin tong exercise later. Okay. But the nice thing about example 34, I included it here because there's an alternative way, an alternative familiar way on how to define the linear map. Here I will assume that you guys know basic matrix arithmetic. So, pwede kong isulat actually si L of V1 to be what? I hope I'll do it right. So alpha, some sort of a matrix product, matrix vector product. So V1, V2. And then, paano ko i-arrange yung mga alphas so that I get the right-hand side here? Probably I'll have alpha 1 here.
Alpha 1,
and
alpha
then
3, alpha 5 ata, sir.
Alpha 2, tama ba? Alpha 3, alpha 4, alpha 5, alpha 6. Then if I multiply this using the usual matrix multiplication, I will get this matrix. Tama ba? Yun yung disadvantage ng medyo nasanay ng gumamit ng software pag-solve ng matrix products, right? But yeah, I guess this is correct. So this is another way of representing your linear map L. The linear map L can be characterized by this matrix, okay? And then we'll see later in Module 4, at the start of Module 4, that any linear transformation can be written as, or can be represented by a matrix. And that's why you will see na almost all of undergraduate linear algebra, even some graduate level linear algebra classes, are focused on studying matrices. Though, as I've said, linear algebra should be the study of maps that preserve the linearity or the structure of vector spaces. But you will see that these maps, called linear transformations, can be represented by matrices. That's why yung ibang courses, bakit nag-start sila sa matrices? Kasi lahat naman daw ng linear mappings, pwede kong i-represent as matrices. So if we study matrices, then we will be able to know the structure of all linear transformations. Because after all, any linear transformation can be represented by a matrix. So that would be the start of Module 4. I'm still writing it. So ang unang part niya ay pagko-convert ng isang linear transformation into a matrix. So, but we'll talk about more of that later. All right. So let's just go on with example 35. So this is a generalization of what I said earlier. So if I have this map, then the linear transformation L sub m is completely determined by a matrix M. And the operation is matrix vector multiplication. So you have a matrix M consisting of aij's. You multiply it with a vector from your domain. You get back a vector from your codomain, and you can obtain that vector from the codomain by performing the matrix multiplication. All right. Okay. Example 36 further generalizes that notion. So hindi lang pala arbitrary na maglagay ka ng matrices. So here you can also define a bunch of linear transformations, Lij. So you will define how many m times n linear transformations. So for each I, for each j, you come up with a linear transformation L sub ij between two vector spaces of V and W. Then the map between the set of m by n matrices over V towards the set of all m by n matrices over W given by this mapping. So ang laman lang nung matrix mo ay yung image nung ijth element nung matrix from the domain ay equal dun sa image ng entry na yon over the or on the map Lij. So we'll see a specific example of a linear transformation of the former example 36 when we go to module 4. But I just put it here as an illustration. Okay. Now, moving on, example 37. So this gives us a linear map that is widely used in differential geometry. though you don't need the differential geometry to play with this linear transformation. So let's see what this example gives us. So here, the domain is the set D, which is the subspace containing all differentiable functions, all right? And then we define the linear map L, okay, such that the image of a differentiable function f under this map is equal to the derivative of the differential of f, okay, defined this way. This would be f prime of a times b for a fixed element of b. And again, the goal here is to show that this is a linear map. So probably I'll show you the proof for this example, showing that this map L is indeed a linear transformation. Okay, let me just open example 37 on another window, or probably my hard copy, para makita ko yung example before I go to another notability page. Okay. So let's try to work out example 37 and show that that is indeed a linear map. Okay, so here we have fixed real numbers a and b, all right? And then the domain of L is the set of all differentiable functions, and the codomain is the set of all real numbers. Let me just double check. I know this is still f bracket. Yeah, f bracket. The function f. So here, sorry, the set curly f. The set curly f is the set of all functions from R to R. So probably I'll mention that as a notation later. So yeah, so the domain is the set of all differentiable functions. The codomain is the set of all functions from R to R. Okay. Actually, I don't need to fix the a and b right now. Okay. And L is defined such that L of f is equal to df for all f in curly f. All right. So pagka in-evaluate ko, ano yung image ng isang differentiable function f under the map L? Probably it would be more familiar to see it this way. Equal lang daw siya sa df, where df is called the differential of f. So where df of AB is equal to f prime of A times B. Okay, now let's prove that this is a linear map. So I will consider arbitrary elements of the domain and an arbitrary scalar over the field or coming from the field. Okay, now what is our field here? Set of all functions. So let's say that my underlying field here is R, because anyway, this is the set of all functions from R to R. So that means it is tacitly assumed that my set of scalars would be the set of real numbers, right? And the first thing is we want to show that addition is preserved, all right? So this is your first bullet. So we want to show that for all f and g in D, the image of f plus g is the image of f plus the image of g. Okay, now let's do that here. Now, and again, to show that these two functions are equal to each other, I need to plug in any arbitrary element of the domain into the left-hand side and show that that is equal to the value over here. Actually, kailangan pala itong i-correct. This is from r squared to r because the domain of the image is r squared. Okay? So again, to show that condition 1 is true, get two elements of the domain of the linear map or the plane or the function that we want to show to be a linear map. So here I am trying to show that L is a linear map. So I get two elements coming from the domain of that map. So they are f and g coming from the set of all differentiable functions. And I want to show that this equation is true, right? But since this is a function, this is another function. So in order to show equality of functions, I need to get an element of the domain of this function. All right? But what is the domain of this function? L of f plus g is an element of f r squared to r. So ibig sabihin, itong function sa kaliwa, ang domain niya ay r squared. And I get a real number back from this function. So I will assume an arbitrary element of the domain of the function on the left. So that would be from r squared. And then I'll plug that into the function, into this function, right? And then by definition, this is the derivative of f plus g evaluated at 80, right? So that's, again, L of f is defined to be the differential of f. So L of f plus g will be the differential of f plus g. But remember, I plugged in the couple AB. So I'll have an AB over here, okay? And then by definition, d of f plus g is given by this guy, all right? So that means that would be f plus g prime evaluated at a times b. Okay? Hopefully, hindi kayo naligaw dun sa dami ng dinaanang substitution. All right? That's why I wanted to start earlier by clarifying how to prove statements about functions. Okay? So again, we want to prove equality of these two guys. But the two guys we are equating there are functions. And the only way to show that two functions are equal is to see if they give off the same images for the same elements of the domain. So since this is a function, I want to plug in an arbitrary member of its domain. But L of f plus g comes from this set, the set of all functions from r squared to r. That's why I took an arbitrary couple of real numbers, plug that into L of f plus g. This is my function, all right? Plug this element of its domain. By definition, f of f plus g is the differential of f plus g. That's why I got the differential of f plus g over here. I plug in ab, so I copied ab there. And then I'll again apply the definition now of the differential. The differential of a function f is defined to be this guy. So just replace f by f plus g. So the differential of f plus g would be f plus g prime evaluated at the number a. That's the first element of your domain of your ordered couple times the second element. Okay? And then I will apply properties of derivative here. Remember that the derivative of a sum is the sum of the derivatives. So basically this will be f prime of a plus g prime of a by properties of derivatives times b, okay? And then I can use the distributive property because R is a vector space over usual addition and usual multiplication of real numbers. So by the distributive property, the b can come into the sum, and I can write it as f prime of a times b plus g prime of a times b. But this is exactly the definition of the differential of f at AB. And the second term is exactly the definition of the the differential of G at the number AB. Okay? But the differential of F at AB is precisely the definition of L of F of AB. And the differential of G is exactly the definition of L of G of AB. And now we have shown that if I plug in AB into L of F plus G, I get AB plugged in into LF plus AB plugged in into LG. And since the choice of A comma B is arbitrary, I can conclude that indeed L of F plus G is equal to L of F plus L of G, which proves that addition is preserved under the mapping L. Okay? Any questions with that? Medyo marami siyang dinaanan, no? Yes, Miss Au?
Sir, so I just got lost dun sa, after you said the reason for the other step, the properties of derivatives, kaya you were able to, uh, uh, from third line, it becomes f prime of a plus g prime of a. So the reason for that is the properties of derivatives.
Right.
That. And then, so yung distributivity is follows from what operation, sir? Is that the distributive property of curly f?
Distributive property ng real numbers.
Of real numbers.
Yep, kasi di ba yung f prime of a, function value ni f prime when you plug in a. So this guy here is a real number. Then
Okay.
ito real number din.
Alright.
Kasi si g prime evaluated at a, b is a real number. So you can think of it as the distributive property of the vector space R over the field R itself. Or you can think of it as the distributive property on the field of real numbers. So either of those two.
Thank you, sir.
Yep. Though probably at this point you don't need to write all of those details, but I see that some of you really got used to including all the all the reasons. So that's a good practice, but probably you can drop some of them if you want. But of course, it's better if you want to justify every line. Of course, okay din siya para pagbabasa nyo or when you do something for your students or create a handout for your students, it would be clear for them. Okay. All right, so that proves preservation of addition. Now let's try if scalar multiplication is preserved. Oh yes, Miss I.
Hi, sir. Question lang po. Yung sa last step, would that be also equal to L of F plus L of G of AB? Or it's okay to stop na there?
Here?
Yes, sir.
Yeah, actually, it's okay to stop here. I guess I'm also guilty of that in some of my proofs because I'm assuming that this is a natural implication. But yeah, it would be a nice thing to include this portion, right? But I hope it is clear that this naturally follows because that this function here and these two functions here preserve assigns to the same ordered pair the same real number. So yeah.
Yes, sir. Okay po. Thank you.
All right. Now let's try scalar multiplication and see if it's preserved. Now let's again. I guess I already said from the top that f is an arbitrary element of the set of differentiable functions, and alpha is an arbitrary real number coming from the field. So here I can start my solution by saying that I want to show that L of alpha f is equal to L of, alpha of L of f, right? And again, I need to plug in elements of the domain of the left-hand side and show that this is assigned to the same value when I plug that real number to the right-hand side, or that couple of real numbers. So here I will let AB then arbitrary couple of real numbers, then L of alpha f, I'll plug in AB, all right? Then by definition, this function is the differential of alpha f evaluated at a comma b, right? So yun yung definition ng L of AF. Lagyan mo lang ng D sa harap yung nasa loob ni L. But what does that mean? This is basically the function inside D, alpha f, take its derivative, plug in the first number in your ordered pair, times b, right? Yan yung definition ni D of f. Kunin mo yung derivative ng function sa loob ni D, i-plug in mo si A doon, then the result, multiply it by b. Okay? Then here I will use the property of derivatives. Ang derivative ni alpha f, alpha being a scalar, is just a times f prime of a, right? So lumalabas yung scalar dun sa differentiation. So I have here alpha times the derivative of f evaluated at a times b. So basically, if you want to be strict about it, this looks like this. Okay. Then you can use associativity of scalar multiplication if you treat R to be a vector space, or simply associativity of multiplication over the field R, right? Either of those two properties will tell us that this can be written as alpha times f prime of A times B, okay? Then if you notice, this is exactly the definition of the the differential of f. So this is alpha times the differential of f evaluated at AB, but the differential operator is exactly the function L. So this is L of f of AB. And now you see here that the function on the left, when evaluated at the ordered pair AB, gives me alpha times the function LF evaluated at AB. So therefore, we can conclude that L of alpha f is equal to alpha of L of f. And that proves that L is indeed a linear operator, or a linear mapping, or a linear transformation, or a homomorphism. Medyo marami ng tawag sa kanya, no? By the way, nakapag-discuss na ba kayo ng homomorphism sa modern algebra?
Hindi pa po.
Okay, yeah. Mamimit niyo uli yung term ng homomorphism later, but in a different context. But in general, homomorphisms are functions that preserve operations on a certain structure. So you will see homomorphism of groups, homomorphism of fields, homomorphism of rings, etc. So that's the same notion. It's just that it so happened that in our case, we are looking at homomorphism between vector spaces. And there are two operations that we need to preserve. We need to preserve the addition and scalar multiplication. Okay. Okay. The next the next example is it's a nice familiar concept that probably we had been used to using since high school or college days. Here I define what the graph of a function is. So if you have any function f between two vector spaces, actually it doesn't have to be vector spaces in general, but here I will confine our discussion about the function between two vector spaces. The graph of f, denoted by grf, is the subset of w that looks like this. Actually, it's not a subset of w. This should be a subset of v cross w. Oh, by the way, that reminds me that if you want to reuse or to keep a copy of the modules, just a favor, at the end of the semester, I will be uploading a compiled and hopefully clean version of the modules kasi marami pang typos time na discover. So at the end of the semester, I'll upload at least a clean copy. I'll try to correct all typos as possible. So if you see some typos, technical or grammatical, just let me know. So para makorek natin, para you'll have a good copy or as good as a copy that it can be at the end of the semester. All right. So the graph of F is basically an ordered pair consisting of the element of the domain and the element of the codomain. So para lang siyang yung usual graph na notion ng graph na alam natin from high school algebra. So for instance, the graph of x squared, though we look at it as as this curve, the parabolic curve here, right? Pero kung kokolektahin mo lahat ng elements ng curve na yan, nandyan si 1, 1, right? Nandyan si 0, 0. Nandyan si 2, 4. Nandyan si square root of 2 comma 2, right? And then it's just, we just collect all of them and produce this nice curve over here. Pero yung idea, yung graph, collection lang siya ng ordered pairs. First component coming from the domain, second component coming from the range. And that's exactly how I define the graph here. Kunin mo yung element ng domain, ang kapartner niya dun sa ordered pair ay yung function value niya under the function f, right? And those ordered pairs collected all over the domain is the graph of f. Okay, and clearly it should be a subset of V cross W. And actually, the graph can tell us something about the linear transformation. So that's in theorem 17. So theorem 17 tells us that if you have two vector spaces over the same field F, then and L is a function from V to W, then L is a linear transformation if and only if the graph of L is a subspace of V cross W. So this is also this is a characterization of linear transformation. As I've said, any theorem that involves an if and only if statement for a concept, that is an alternative definition. All right. So if we want to prove it, we need to prove two assertions. Number one, L is a linear transformation, implies the graph is a subspace, and the other way around. If the graph is a subspace, then L is a linear transformation. Then let's read over the proof and see how it is done. Okay. Now let's start with a forward assertion. That is, we assume that L is a linear transformation, and we want to show that the graph is a subspace. And I hope you still remember the easy way how to show that a certain set is a subspace. We use the compact criterion. I think it's theorem 3. Okay, and that's what I want to do here. But first, I want to say that clearly GRL is a subset of V cross W, right? Because by definition, first elements come from V, second elements come from W, right? And then I will take two arbitrary members of the graph of L and show that their sum is also an element of the graph. Okay. Now, this is my first, this is my second arbitrary element of the graph. I will add them, and hopefully it should be clear that it also belongs to the graph of L. Okay. Now, usual vector addition, I get this guy. Okay. And you see that since L is a linear, since we assume that L is a linear transformation, L of V plus L of V prime becomes L of V plus V prime. Again, we can do that because L is assumed to be a linear transformation. So this sum becomes this guy. All right. And what do we have here? If you look at this guy, yung first component niya ay V plus V prime, nanggagaling siya kay curly V. Pero yung second element, function value ng first element. Right? And so I am sure that this guy is an element of the graph of L because its first component is coming from the domain. The second component is the function value under L. So definitely by definition 7.1, sorry, not definition 7.1, but by the definition of the graph of L, this guy is an element of GRL. So that means vector addition on the graph um, is closed. Sorry, it's the other way around. Addition. The graph is closed under addition. So yung set yung closed under dun sa operation. Okay. Let's try the other one. The next part is to show that the set is closed under scalar multiplication. Again, I get an arbitrary scalar, multiply it to an element of the graph, okay? And then by using the usual scalar multiplication, each component is multiplied by alpha. We got this guy. But again, we assume that L is a linear map. So if you look at the second component, the alpha here, the scalar alpha, can go inside L. Okay? And that's how I got this. And then let's examine this ordered pair. The first component is alpha v. The second component is the function value of alpha v. That means this satisfies the definition of the graph of L. So this ordered pair belongs to the graph of L. Okay, and we have shown that the graph is closed under both vector addition and scalar multiplication, and so by the compact criterion, GRL is a subspace of V cross W. All right. Now the converse. Let us see if that is easy. The converse, i-assume ko naman na yung graph ay subspace of V cross W. Gusto ko namang ipakita na si L ay linear transformation. And now, in order to do that, I need to show that the conditions of definition 7 are both satisfied. Okay? All right. So first, I'll work out what the assumption means. So here we are assuming that GRL is a subspace. So that means if it is a subspace, then the sum of two elements of the graph must also be in the graph. So I just wrote down what it meant. Okay. So ideally, again, kukuha ko ng dalawang elements ng graph of L. Gusto kong ipakita na si L ay magiging linear map. But in order to do that, I need to take advantage of the fact that we assume that the graph is a subspace. Okay. And one implication of being a subspace is that if I take two elements of the graph, then their sum by theorem 3 or by the compact criterion must also be in the graph of L. So if I add this guy and this guy, I'll get V plus V prime. Second component is LV plus LV prime, then that should be in the graph of L. Okay? Note that for now, I cannot write this as L of V plus V prime because I am not sure if L is a linear transformation. That's what we want to show, okay? But I can do that because remember by definition of the graph, first component nanggagaling kay domain. Ano yung requirement para sa second component ng elements ng graph? Dapat yung second component ay yung function value ng first component. Eh sinabi ko na that this ordered pair belongs to the graph of L. So ibig sabihin yung second component, dapat siya yung function value ng first component. So the second component, there you go, should be the function value of the first component under the function L. So that's why I am able to say that L of V plus V prime must be L of V plus L of V prime. All right, so that means addition is preserved in L. Okay, now let's try scalar multiplication. Now for scalar multiplication, I'll do the same trick. I want to take advantage of the fact that the graph is closed under scalar multiplication. So if I get a scalar, multiply it to an element of the graph, I'll do usual scalar multiplication for the cross product of two vector spaces. So that means each component will be multiplied by alpha. But remember that the graph is closed under scalar multiplication. So the product here should be in the graph of F. But again, how does the graph is how do we define the graph? Well, the graph was defined to be the first component should be coming from the domain. The second component must be the function value of the first component. So the second component must be the function value of the first component. That happens, or that is required whenever you have an element of the graph. And so if you write that down, you'll get L of alpha V is equal to alpha of LV. And so therefore, L is a linear transformation because we have shown that vector addition and scalar multiplication were preserved. All right. Any questions, Don? Medyo gusto ko itong i-discuss kasi parang hindi obvious yung galing ka dito. Bakit nag-follow ito? So that's why I wanted to state to discuss it verbally. Kasi hindi ko sinulat yung detailed reasons there. But I hope the reason is clear. I just worked with the definition of the graph of L and the fact that we assume that the graph is a subspace. Okay. Now here, I just introduced a notation because I think I forgot to mention it in the previous module. So just a shorthand, since we'll be dealing with functions here. We will denote the set of all functions from a set X to a set Y to be curly f of xy. So see curly f of xy, set of all functions from X to Y. Okay. Now, in the next result, I introduced this set, hom of VW. This stands for the set of all linear transformations coming from V to W. So lahat ng posibleng linear maps, kukolektahin ko lang into a set. I'll call that set hom of V, W. It is called that way because remember we said that linear transformations are also called homomorphisms. So hom is short for homomorphism. Or if we wish to emphasize the underlying field, we can also write hom sub f of V, W. Okay. And the nice thing is that if we will collect all the linear transformations, they form a vector space under the usual function addition and scalar multiplication, and that is given in proposition 18. Now to prove proposition 18, you can do it in several ways. One way is to use the definition of a vector space and show that all, I think, 6 or 7 properties of a vector space is satisfied. But I guess the proof uses a familiar trick. So since I know that hom of VW is a subset of the set of all functions from V to W, right? And I know that under the usual function addition and scalar multiplication, the set of all functions form a vector space. So it suffices to show that hom of VW is a subspace of the set of all functions, all right? At gusto kong gawin yon kasi mas madaling mag-prove ng subspace siya. At kung subspace siya, it follows that it is a vector space on its own right. Okay? And that's what I did here. Let's see how the proof went. So again, that's the strategy. Instead of using the definition for a vector space, I used the compact criterion because if the two conditions of the compact criterion are met, then automatically your subset is a subspace and hence a vector space on its own. So first I noted that hom is a subspace of the set of all functions. Okay, and I want to show that it is closed under vector addition and scalar multiplication. So what I did is to take two elements of hom f, or two arbitrary linear transformations, and I want to show that this is closed under addition. So let's see. So I want to show that L plus L2 is also a linear transformation. And again, the definition of linear transformation tells us that addition should be preserved. So I'll take L1 plus L2. I want to show that this is a linear transformation, so I plug in V1 plus V2 into it, where V1 and V2 are coming from the set V. And then by definition of usual function addition, L1 plus L2 of V1 plus V2 is equal to the function value under L1 plus function value under L2. Okay? But since we assume that L1 and L2 are linear transformations, then I can use the linearity property with respect to vector addition. So L1 of V1 plus V2 is equal to this sum. And similarly for L2. Okay? And then since this guy, this guy, this guy, and this guy are elements of the set W, and W was assumed to be a vector space, then I can appeal to associativity and commutativity of addition on W and regroup some terms and come up with this. Why do I want to do that? Because here I am evaluating the same element with respect to L1 and L2, and then I'm adding them up. This is exactly the definition of L1 plus L2 of V1. And similarly, this guy is the exact definition of L1 plus L2 of V2. And here I was able to show that if I plug in any arbitrary element V1 plus V2 of the domain into L1 plus L2 and and plug in V1 and V2 individually and add them up, I get the same thing. And so I say that L1 plus L2 is of V1 plus V2 is equal to this plus this, which is basically the first criteria for being a linear map. And then I move on to the second part. For the second part, I want to show that scalar multiplication is preserved. So I'll take the sum. Again, I'm testing if L1 plus L2 is a linear map. So I'll take L1 plus L2. I'll plug in a scalar multiple of V1, say beta V1. Then by definition of addition on functions, this is just L1 of beta V1 plus L2 of beta V1. And then by linearity of L1 and L2, I can take the scalar out. So take the scalar out, take the scalar out, because again, our assumption is that L1 and L2 are linear maps. So we get this guy. And then by distributivity of multiplication over addition in the vector space W, I can factor out sort of beta, right? And come up with this guy. And what do we notice about the thing in the brackets? This is exactly the definition of the function value of V1 under L1 plus L2. And again, it seems here that instead of taking the image of a scalar multiple, we can just take the scalar multiple of the image. So therefore, scalar multiplication is preserved in L1 plus L2. So this means L1 plus L2 is a linear transformation. So that means the set Hom F is closed under addition. But don't forget, we also need to show that it is closed under scalar multiplication, because I'm showing that Hom F is a subspace of the set of all functions. Okay, so I check if this set is closed under scalar multiplication. And to do that, I'll see if alpha L1 is a linear transformation. And how do I check if a function is a linear transformation? Plug in a sum of two vectors. Okay, alpha L1 of V1 plus V2, by definition, is alpha times the function value of L1, the function value of V1 plus V2 under L1. And then I assume that L1 is a linear map. So I can apply the linearity property. So I can evaluate V1 and evaluate it at V2 independently, then just add the results. And then I'll use distributivity of scalars over the vector sum. So that's why I was able to write it this way, okay? And then again, this is exactly the definition of alpha L1 times V1 and alpha of L2 V2. Actually, parang dito kinailangan ko siyang gawin ng magkahiwalay. Yeah. But essentially, this tells us that yeah, vector addition is preserved under alpha L1. And then the last portion of the proof is to show that scalar multiplication is preserved in alpha L1. Again, para hindi tayo nawawala dun sa goal natin, paulit-ulit yung sinasabi, gusto ko ipakita si alpha L1 ay linear mapping. So para maging linear transformation or linear mapping, i-plug in ko dapat kay alpha L1 ang isang scalar multiple ng isang vector. Right? But by definition, this guy is equal to this guy. Yung alpha, ipang-multiply ko lang dun sa function value. But L1 was assumed to be a linear map. So that means the scalar beta can come out and be in front of L1. And then by associativity of scalar multiplication in the vector space W, I can write it this way. Okay. And then commutativity, I'll just reorder the alphas and the betas. And then I'll use associativity of scalar multiplication in W para mag-group ko yung alpha at saka yung L1 V1. Okay? But this is exactly the definition. This is the definition of alpha L1. So that means alpha L1 of beta V1 is equal to beta times alpha L1 of V1. So that means scalar multiplication is preserved in alpha L1. And that proves that alpha L1 is also a linear map. Therefore, the set of all linear maps is closed under vector addition and scalar multiplication. And so Hom F is a subspace of the set of all functions by theorem 3. And since it is a subspace, it is a vector space on its own right. So that completes the proof. Okay. Medyo maraming pasikot-sikot yung proof. I hope you didn't get lost there. Actually, kahit ako nung sinusulat ko yung proof, kailangan kong balik-balikan. Ano nga ba yung gusto kong ipakita? Sino yung gusto kong ipakita to be a linear map? Paano ko mapakita na linear map? Kasi magkamukha yung mga arguments. So, but it should be clear that I need to show 4 things, right? Because I want to show that L1 plus L2 is also a linear map, and alpha L1 is also a linear map. And for each of those 2 proofs, I need to check whether the conditions for a linear map are both satisfied. So kaya naging 4 yung parts ng proof. All right? Any questions? Or na-lost ba kayo somewhere in the middle? Kasi nawala na yung mga nagre-react ng thumbs up kanina. But it's fine. So kung medyo na-lost kayo, you can take time later to read the module to read the module, familiarize yourself with how linear transformations are defined, and then try to reread the proof. I try to include as many details as I can there, so you can reread the proof, so that you will be guided how to write your own. Okay. But the important thing here is you should be familiar on how to show that a given map is a linear transformation, because again, a majority of the items and the in homework 4 will require you to show that certain maps are indeed linear transformations. Okay. All right. So do you guys have questions so far? Because I am thinking to stop right here. Because probably some of you are still working with homework 3, so you might not have the time to look at module 3, and things will be more complicated starting from theorem 19. though not too much, but if you haven't read or if you're not yet familiar with the definition of linear maps, it might be difficult to follow the discussion about Theorem 19 and the rest. So I suggest we stop here and then talk about the remaining of the modules starting on Saturday. Is that okay? Kasi gusto kong you familiarize yourselves muna with uh, checking if a certain function is a linear transformation. Any objections?
None, sir.
Wala naman?
Answer.
Or pagod na kayo?
Ano po?
Medyo napagod na rin ako with the proofs that we did. Kahit medyo binabasa ko lang siya, medyo nakakapagod din siya.
Oh, sir,
Mahaba po kasi, sir.
Overload na.
Ang dami-daming
Mathematical overload na, sir.
Yun yung problema ko tuwing mid-year. Kaya usually kahit sa UPLB before I left, nung medyo naging senior ako ng konti, na nagkaroon ako ng karapatan na humindi sa mga classes na i-offer, I always refuse teaching in the summer kasi or in the mid-year kasi napaka-compact ng time frame. And I believe ang math hindi siya yung biglaang subject. Hindi siya pwedeng pag-aralan ng isang upuan. Yeah, that's why I tried my best to stretch the semester with you guys kasi alam kong mahirap. And I really appreciate all the effort that you put into the course. And I actually saw the improvement for most of you. So yeah, good job, guys. So yeah, overload, I agree. So let's stop here and talk about the remaining parts. Probably we can spend 2 more meetings with this. Hindi naman ako nag-rush. Oh yes, Sir Edelmar.
Sir, maganda naman yung explanation mo, sir, pero kasi nahirapan ako to follow the flow. Pwede, sir, humingi ng hint, sir, for example, sa homework for kung ano yung suited na doon sa given examples para at least I could have to follow the flow kasi doon ako nahihirapan, sir. Talagang kasi pagkagaya nito sa homework number 4, problem number 1, ano kaya ang tamang suited na doon sa example kasi doon ako magfa-follow.
Okay,
Salamat,
sure.
sir, ha.
Yep. Yeah, let's see. Yeah, I was about to suggest that na siguro tingnan natin yung homework for ano yung mga pwede na nating sagutan or pwede nyo nang simulang sagutan by just the definition of linear transformation. So, and then probably we can probably start the solution so you will be guided on how to do it. Let me just scroll down to homework 4. Typo pala yon kasi it should be homework 4. I think in the uploaded copy, I wrote homework 3 pa din. So this is homework 4. Let me see. Unfortunately, problem 1 requires the notion of the inverse image, which we haven't tackled yet. So I'll skip it for now. Okay, probably we can do problem 2 or outline the solution for problem 2. Let's see. Siguro na napansin nyo na dun sa mga items na medyo nagbigay ako ng hint, depending dun sa details ng hint na binibigay ko, medyo nagiging mahigpit ako in grading your work on those particular topics because my assumption is I gave you some hints, so I expect a more detailed solution para alam ko lang na hindi nyo lang kinopya or sinulat yung hints na binigay ko. So, kaya minsan yung mga estudyante, sila yung umaayaw na magbigay ako ng hint. But I hope, yeah, you include as much details as possible in your homework, right? So here, ano yung gusto nating ipakita? So, si f daw ay isang continuous function such that f of x plus y ay equal kay f of x plus f of y for all x and y in R. And I want to show that f of x is a linear map. Okay? Now, remember, for f to be a linear map, may dalawang bagay na dapat masatisfy from the definition. So for f to be a linear map na lang yung tatawag ko instead of a linear transformation kasi masyadong mahaba yung transformation. But linear maps and linear transformations or homomorphisms are the same. So dapat masatisfy niya to. F of x plus y is equal to f of x plus f of y for all x, y, and r. And f of alpha x is equal to alpha fx for all x, y, and r. Okay, so and I guess the first part is already done for you by assumption. Kasi nandun na sa assumption na si f of x plus y ay equal kay f of x plus f of y sa kahit na anong real numbers x and y. So the first half is done. Now, how can we show that yung second condition is met, that scalar multiplication is satisfied, right? So we want to show, or what remains to be shown, is that f of alpha x is equal to alpha of f of x. Gisip ako ng paraan paano hindi ko siya may spill yung hint ng todo. Pero one way you can do, or one thing you can do is to use the fact that you already know that this is true, right? By assumption. So pwede mong i-distribute sort of yung addition, take it out of the function evaluation. So think of a way how can you write alpha x as a sum of two real numbers. Remember, this should be a little bit more familiar because the set here is just a set of real numbers. So the clue is, think of a nice way on how to write alpha x as a sum. Kasi alam ko na yung sum ay na-preserve under the mapping f. So kailangan ko nila ipakita, scalar multiples are also, or scalar multiplication is also preserved in f. So ibig sabihin, I need to think of a way how to break alpha x into a sum. Kasi yun pa lang yung alam ko eh. How to deal with the function value of a sum. So if I can somehow write alpha x as say y plus z, and you need to give me how y and z looks like in terms of alpha and x, all right? So magagamit mo yung f of alpha x, pwede mo siyang isulat as f of y plus f of z, right? I mean, not directly that, but probably something like this: f of x plus y. Y plus z. So find a way to write alpha x to be equal to y plus z. Again, in your work, I want you to give me what y is and what z is in terms of alpha x, in terms of alpha and x, all right? So itong right-hand side, puro alpha at x lang dapat yung makikita ko. But the idea is to break alpha x down into the sum of two real numbers, okay? And then you can use the fact that it preserves sums. So pwede mo itong sulat as y plus z by assumption y plus f of z. All right, and then use the fact that f is continuous somehow in your argument, fit in the assumption that y is continuous so that you can build this up together to become alpha of f times x. Okay, so the jump from here to here is basically using a clever breaking down of alpha x, and then the jump from here until here will use the continuity of the function f. Okay, So try to organize your thoughts about this. Though this is just one way of proving it. That's how I think of solving this. How I thought to solve this. But you can think of other ways. But if you want, you can take this clue out. Uh, Try to write it on your own, and then let's see on Saturday if you had some troubles using this argument. All right.
Thank you,
So yun
sir.
yung naisip ko solution. Yep.
Thank you.
Yes, Sir Edelmar.
I'm satisfied, sir. Thank you.
Yeah.
Nice discussion, sir. Thank you.
Right. For number 3, it involves the kernel. So let's skip this one. And then yeah, probably the first part of problem 4 can be done. Show that this is a linear transformation. But again, all you need to do here is to show that addition is preserved, right? So say let x and y be real numbers. Then look at LF. No, not subspace of W containing differentiable function. L is a map from W consisting of all differentiable functions. So for this one, I need to get, I want to show that L of F plus G is equal to LF plus LG. You can pattern your solution here to the differential thing that we have shown earlier. Medyo mas komplikado nga yung kanina kasi yung function value ni L. Remember the example that we have LF equals DF of AB. This is LF of AB equals DF of AB equals F prime of A times B. It follows in a similar fashion, except that what you need to plug in is just a real number because LF of x is defined to be F prime of x plus cosine x times F of x, all right? So you want to show this. In order to show this, you need to evaluate L of F plus G of x, all right? And again, by definition of L, this would be what? The derivative of the function inside L. So it's going to be f plus g prime of x plus cosine x times f plus g of x. All right. And try to manipulate this one and show that this is equal to L of f of x plus L of g of x. So show that this, after some computations, is equal to LF of x plus LG of x. That's how we show it preserves addition. And then for multiplication, just put that here. You want to show that alpha, that so ipakita siya a linear map. So I want to show that L of alpha f is equal to alpha of LF, right? So what I'll do is to compute L of alpha f of x. Again, by definition, this is alpha f prime of x plus cosine x times alpha f of x. Let me just double check that. Yeah. Derivative nung nasa loob ni L plus cosine times yung nasa loob ni L. So here, I have derivative nung nasa loob ni L evaluated at x plus cosine times yung nasa loob ni L times x. And then you need to show, after some computations, that this is equal to alpha times LF of x. All right? Probably just using properties of derivatives. And then let's talk about the kernel next time. Okay. And then for problem 5, yung map naman dito ay from the set of all 3 by 3 matrices with real coefficients. with real entries to the set of all real numbers. Ng mapping ay ang L of a matrix ay yung sum ng lahat ng elements ng matrix. For instance, if you want to get the image of a 3 by 3 matrix, like say the identity matrix 1 1 1 0 0 0 0 0 0, ang image niya lang under L ay yung sum ng lahat ng components. So i-add nyo lang lahat ng entries. So that's what this double summation tells us. So ang L of 3, ang L ng identity matrix ay equal kay 3. Obviously, ang L ng zero matrix would be 1. This would be the zero vector in the codomain. But the codomain here is the set of all real numbers. At sa vector space na yon, true enough, ang zero vector ay 0. And you can verify na, oh, yeah, that's true, because the sum of all entries of the zero matrix is equal to 0. Okay? And then, yeah, you can check that it is a linear transformation by, say, looking at L of, say, A, B, C, D, E, F, G, H, I, plus, or it could have chosen a better naming for the entries kasi 18 pala yung kailangan ko dito. Mauubos na yung letters ng alphabet. J, K, L, M, N, O, P, Q, R. Gusto kong ipakita ito ay equal lamang kay L of this guy plus L of the second guy. And that would be straightforward calculation. So gusto ko lang makita kung paano nyo i-construct yung solution. But I guess the proof is pretty straightforward. Okay. And also for scalar multiples. So for scalar multiples, meron ka lang L of alpha A, B, C, D, E, F, G, H, I. Gusto natin ipakita this is just alpha times L ng A, B, C, D, E, F, G, H, I. Right? And I hope you can imagine how it will work. I guess this is pretty mechanical, straightforward, but I want to see how you will write the arguments, okay? Because I'm treating this not necessarily a technical course, but also an exercise for you to write proofs. So probably some of you didn't have the experience of writing proofs or did write proofs, but a long time ago. So maganda rin siyang refresher, okay? All right, and then you will find the nullity of L, but we haven't talked about the nullity of L yet. So, but yeah, let's talk about it next time. Okay, any other questions before we go? Yeah, don't worry kung medyo mahirap sumabay sa meeting ngayon, especially if you haven't read the modules yet. So you'll have a couple of days before we meet again on Saturday, same time. Pero hopefully by then you have read at least the part of the module that we have just discussed today, so that you can participate when we talk about more technical things about the kernel, the range, the nullity, and the rank of linear transformations. All right? Okay, other concerns? By the way, guys, open na rin yata yung student evaluation of teachers. So I'll really appreciate it if you'll accomplish the evaluation of the course and of me with your honest opinion. So because it will greatly help me how to improve my teaching. All right. Other concerns?
Tapos na po ako sir nag-evaluate sir sa evaluation sa SIT.
Okay. Yeah. Thank you, sir.
Salamat sir sa magandang process learning.
Yes, Miss I.
Hi, sir. So for homework 4, we need to answer all 5.
Yes.
Okay.
Kailangan ba magbawas? Well, nakita ko na yung mga thumbs up. Nabuhay yung mga thumbs up, no? Okay, yeah, let's talk about it on Saturday. Pag-usapan natin sa Saturday. Try nyo muna put your hands into it, and then let's see. But sige, ganito yung gawin natin sa homework homework 4. Um, Gagawin kong, kasi during previous homeworks, pag nakalampas na kayo ng required submission, halimbawa pinaunti natin yung required number of submissions. Pag nakalampas na kayo, hindi ko na gine-gradean. So, for this homework, probably what we can do para na rin pambawi with the previous homeworks, because I guess some of you are really disappointed with your scores in homework 1 and homework 2. Though I'm very satisfied with the effort you put into it and your grades, homework 1 and homework 2. But if you feel you want to make bawi with your scores for those two homeworks, yeah, I'll grade all 5. But let's talk about what would be the perfect score, right? So, posibleng hindi over 25. Probably I'll still challenge you guys to answer all 5 points each, but probably lessen the denominator to say just over 20 na lang siya. So because I think you still have some time, enough time to try to answer all 5 of them, and then say if you get perfect on 4, and then medyo an an incomplete attempt on the 5th problem, so probably you can get a 23 out of 20, or even I can go as low as 15. But I want you guys to first try homework 4, and let's talk on Saturday on how we can sweeten the deal with homework 4. All right?
Okay, sir. Thank you, sir.
All right. Pero yeah, para hindi masayang effort ng mga gagawa. So yeah, I'll grade everything for homework 5. And then let's just agree on what the denominator would be. And of course, you have your usual markup, 20% of your grade. So yeah. Okay. Any other concerns or proposals? Wala pa pong proposals? Okay. Yeah, let's talk again on Saturday. Pag na-try nyo ng sagutan, and let me know kung medyo mahirap, and then yeah, let's talk about it more. All right, if that's all for today, so yeah, thank you guys for coming today, and hope you enjoy the rest of the day. Bye, guys.
Thank you, sir.
Thank
Yes,
you,
sir. Thank
sir.
you.
Bye, sir.
Bye bye.